Hello everyone, this is Mounika Girireddy from MultiCASE. Welcome to today's session. In this session, I'm going to present on QSAR models for endocrine disruption. Endocrine disrupting chemicals are substances in the environment, food sources, personal care, and manufactured products that interfere with the normal function of your body's endocrine system and cause various developmental, reproductive, and neurological effects. Since the endocrine disrupting chemicals come from many different sources, people are exposed in several ways, including the air we breathe, the food we eat, and the water we drink. Endocrine disrupting chemicals can also enter the body through the skin. You might have heard several times in vivo and in vitro terms associated with endocrine testing. Why do we need both of them? It is because we consider a chemical as endocrine disruptor if it has an adverse effect which is in vivo, and this adverse effect is linked to a mechanism of action which is in vitro. In vitro provides information on molecular interactions and mechanisms at cellular level, whereas in vivo reflects responses from living organisms. Since this is one of the complex endpoints for testing, OECD, as an initiative, developed a conceptual framework for the screening and testing of endocrine disrupting chemicals, which helps to interpret the assay results and suggest possible additional studies for reducing uncertainties. We will discuss in detail about this in our upcoming slides. In this webinar, we would like to provide an overview of the available OECD conceptual framework, discuss what role QSAR plays in this framework, and propose a methodology that maximizes the use of in vivo data by using in vitro data. Since many of us have confusions on how to determine an endocrine disruptor, how to test it, how can we interpret the results, this conceptual framework developed by OECD gives us ideas about where to start testing. This framework, with levels from 1 to 5, is not a test strategy to be followed linearly from level 1 to level 5. It assists in endocrine relevant tests with data interpretation in the light of information that may already exist, and to provide optional suggestions for obtaining additional data, if required, to increase confidence in conclusions on the endocrine disrupting possibilities of a particular chemical. And this framework will be updated as new assays are developed. Levels include both mammalian and non-mammalian toxicology assays, but we are concentrating on mammalian studies today. Level 1 evaluates existing data and what kind of data is suggested from levels 1 to 5. Now let's understand each level in detail. Level 1 evaluates existing data and existing or new non-test information, which includes physical chemical properties, ecotoxicological data from standard, non-standard tests, read across, QSAR, in silico predictions, ADME predictions. Here are few examples of how they are related to endocrine predictions. Lower molecular weight compounds have higher likelihood as disruptors, as they can easily penetrate and interact with hormone receptors. Ecotoxicity examines effects of chemicals on various organisms, as some species may be more susceptible to certain chemicals due to variations in metabolism. Structural analogs from QSAR models helps in predicting mechanisms and endocrine activity. How chemicals are absorbed, distributed, metabolized, and eliminated from the body can influence their potential to interact with the endocrine system. Coming to level 2 deals with in vitro assays providing data about selected endocrine mechanisms or pathways. For example, receptor binding assays, receptor transactivation assays, steroidogenesis, aromatase assays, high throughput screens, etc. Here, for example, in screening assays, positive in vitro test results provide information about endocrine mechanism or mode of action and indicate a possibility of endocrine disruption effects in vivo. Results from the combination of all these tests will increase weight of evidence. Level 3 is about in vivo assays providing the data about selected endocrine mechanisms. These include uterotrophic assay and Hirschberger assay. These assays provide yes or no about the ability to interact with estrogen androgen receptor mediated modalities. Level 4 includes in vivo assays providing data on adverse effects on endocrine relevant endpoints, like repeated dose 28-day study, repeated dose 90-day study, reproductive and developmental toxicity screening test, 28-day inhalation toxicity study, etc. come under this level. These assays help in more thorough assessment of possible or actual endocrine disrupting effects, indicating possible adverse effects. Finally, level 5. In this, the in vivo assays provide more comprehensive data on adverse effects on endocrine relevant endpoints over more extensive parts of life cycle of the organism. This level includes extended one generation reproductive toxicity study, two generation reproduction toxicity study. All these data add to the weight of evidence concerning potential for impacts in humans and vertebrate wildlife. So, by using data or predictions from all these levels, we can gain confidence in our conclusions regarding the compound to be an endocrine disruptor or not. As we discussed in previous slides that there are multiple assays associated with endocrine in each level, this slide gives you an idea of what models we have in Qsar and Qsar Flex that can support various levels of this framework. We have physical chemical properties which include log P, water solubility, vapor pressure, boiling point. For ecotoxicity, we have bioconcentration factor, ready biodegradability, soil absorption, daphnia, fathead menu, honeybee, algae, tetrahymena. Our model bundle also includes ADME properties like extension of metabolism, oral bioavailability, urine excretion, volume of distribution. Coming to high throughput screens, we have androgen, estrogen, thyroid, and aromatase models. Our in vivo assays include uterotrophic and Hirschberger. Other in vivo assays like rat oral subchronic, carcinogenicity, reproductive, and developmental are also available. Now that we have an understanding on various levels in the conceptual framework, let's concentrate more on in vivo and in vitro assays and building QSAR models with them. There is a lot of data available for in vitro modeling from TOX21 high throughput assays, which cover several mechanisms associated with endocrine disruption. But when we check for the in vivo data, the availability of data is very low, like 34 compounds for uterotrophic, 25 for Hirschberger agonist, and 42 for Hirschberger antagonist. This made us think of developing a methodology that uses the in vitro QSAR models and predict the in vivo outcomes, thereby increasing the availability of in vivo results, which can in turn reduce animal testing. Since the in vivo data was very low, it was difficult to build a model with conventional techniques. Several QSAR models were developed that are associated with various mechanisms like androgen and estrogen agonist, antagonist, thyroid, and aromatase. For developing in vivo models, we restricted to using estrogen and androgen receptor based QSAR models. We concentrated on uterotrophic and Hirschberger in vivo assays. Uterotrophic is a short term assay conducted in female rodents which identifies chemicals with changing uterine weights. Hirschberger assay reflects androgenic and anti-androgenic activity with weight changes in androgen-dependent tissues like ventral prostate, seminal vesicle, and so on. Our methodology consists of two steps. In the first step, we build fragment-based statistical QSAR models associated with various in vitro mechanisms like estrogen and androgen agonist, antagonist, and binders. We then developed naive-Bayes models using the outcomes of in vitro models for parameterization and the in vivo outcomes from uterotrophic and Hirschberger assays as dependent variables. Since we had multiple models, let's say for uterotrophic, we had 7 models like estrogen agonist, agonist alpha, agonist beta, antagonist, antagonist alpha, antagonist beta with several mechanisms. We applied variable selection and selected 3 models among all these 7, like estrogen agonist alpha, and estrogen binder for building uterotrophic model. For Hirschberger, we don't have the problem of many models, so we directly chose androgen agonist and androgen antagonist without any variable selection. This slide shows the in vitro QSAR models we developed and the respective training set sizes. We have rat, human, and mammalian models. We used Qsar software for building all these in vitro models. You can see that we have androgen agonist, antagonist, estrogen agonist, antagonist, binder models, thyroid and aromatase models, aryl hydrocarbon models. Models training set sizes range from 885 to 20,763. Most of the data for these models was collected from Tox21. You can see that the models perform pretty well with external validation metrics ranging from 61 to 91% sensitivity, 61 to 87% specificity, and 0.66 to 0.89 ROC. Similarly, for the bootstrap cross validation, we have 63 to 94% sensitivity, 68 to 92% specificity, 0.86 to 0.96 AUC. For all these models, we have QMRFs and they also follow OECD principles. These are the validations for the in vivo naive Bayes models. You can see that there is a slight improvement in the validation of uterotrophic from 90.5 to 90.9 sensitivity, 76.9 to 83.3% specificity, 85.3 to 88.2% accuracy when we applied variable selection and chose specific models rather than using all the available 7 models. For Hirschberger agonist, we have 50% sensitivity, 100% specificity, 80% accuracy. And for Hirschberger antagonist model, we have 66.7% sensitivity, 73.3% specificity, and 69.1% accuracy. No external validations were performed for Hirschberger models due to the lack of data. For uterotrophic, we were able to get a small data set of 9 compounds and predicted it against our model. All the compounds were predicted accurately. This is an example of how we calculated predictions of in vivo from in vitro. You can see that when bisphenol AF is predicted against estrogen agonist alpha, and binder models, it was evaluated to be known positive, and positive respectively. When these outcomes from the in vitro models were plugged into the naive Bayes model, value of minus 0.52 was obtained for being positive and minus 2.437 for being negative. As the negative value is substantially lower than the positive value, bisphenol AF was predicted to be a uterotrophic positive compound. Estrogen activity related structural alerts were also identified, which are highlighted in red in this structure, and these alerts strengthen our predictions. Table above shows some of the Bayesian probabilities calculated using several conditions like the compound to be in vivo positive, in vivo negative, compound being in vivo positive given a positive outcome from an in vitro QSAR model, etc. These probabilities are then used in our algorithm for calculating predictions. I would like to show a small case study on diethyl stilbestrol. From the in vitro predictions, we can see that it is not an androgen agonist, but it is positive in androgen antagonist and estrogen related models. Also, it has positive outcome in thyroid antagonist and aromatase inhibition models. Most of the results are known positives, which indicates the compounds are present in the training set. These predictions indicate that there can be adverse effects like, for example, increased risk of breast or uterine cancer because of estrogen agonist, infertility or depression because of androgen antagonists, vaginal atrophy or hot flashes because of estrogen antagonist, hypothyroidism because of thyroid antagonist, etc. When we check the in vivo predictions, they came out to be uterotrophic positive, Hirschberger agonist negative, Hirschberger antagonist positive, which indicates possible adverse effects like uterine weights change, reduction in androgen stimulated weights of ventral prostate, seminal vesicle, etc. These in vivo predictions reflect the in vitro predictions, and we can see that we have most of the estrogen activity like agonist, antagonist, and binders positive in vitro, and it is positive in uterotrophic too. Similarly, for negative androgen agonist, we have Hirschberger agonist negative, and for positive androgen antagonist, we have Hirschberger antagonist positive. All these predictions of in vivo and in vitro increases the chances to consider this compound as endocrine disruptor. Also, when we check the structural alerts, we have phenol, and hydroxyl groups, which serve as indicators of endocrine disruption. The presence of these phenol and hydroxyl alerts also strengthens the chances to consider this compound as endocrine disruptor. Out of curiosity, we tested this compound on the models we had. The predictions came out to be positive in carcinogenicity models, indicating the presence of several adverse effects like cancer sites in uterus, thyroid glands, ovary, pituitary glands. Reproductive and developmental models related to female and male fertility also turned out to be positive. All these adverse effects reflect our in vitro and in vivo model predictions, suggesting diethylstilbestrol to be endocrine disruptor. So, each set of predictions or data strengthens the analysis of compound to be either endocrine disruptor or not. It is difficult to use the outcomes from one of the model and conclude to be positive or negative endocrine disruptor as we do usually with other endpoints. So, to conclude, this case study we gathered data and predictions for the compound based on various levels of information from OECD conceptual framework and tried to analyze them. All these predictions and data increase the confidence in our conclusions and serve as weight of evidence. Another example here, endosulfan. This case study is used to show a limitation of in vitro models' false positive predictions. If you see the androgen agonist model, it was predicted as positive. Androgen antagonist and estrogen models were also predicted as positives. When we see the in vivo model predictions, they turned out to be negative for androgen agonist, which indicates a conflict with the in vitro. Here are the structural alerts for the compound. From all these, we can see that there is a conflict between in vitro and in vivo outcomes, and the output of in vitro model for androgen agonist can be a false positive. In these cases, where we have false positives in vitro models, in vivo outcomes and structural alerts can help to some extent in the analysis and help us detect those false positives. Coming to the limitations, as we discussed in the previous slide, the in vitro models can produce 12 to 47% of false positives, but the in vivo predictions and the alerts can compensate these false positives and help us in the analysis. Since the dataset sizes of in vivo assays is very less, like 34, 25, and 42 compounds for uterotrophic, Hirschberger agonist, and Hirschberger antagonist, respectively, the performance of these models can still be improved. And although the approach shows promise, additional external validation is needed, especially for the Hirschberger models. Even though we cover several mechanisms in these in vitro assays, there is always a room for the addition of new mechanisms, and this needs continuous learning and updating of the model bundles. Because of its complexity, deciding on the final outcome of endocrine disruption is always difficult. You can feel this from the framework and the assays they included. To conclude, we discussed the OECD conceptual framework, which consists of various levels, thereby providing an idea of how to interpret the test results for endocrine disruption. We also discussed various QSAR models, which can be used as weight of evidence for determining endocrine activity of a compound. The methodology developed using in vitro models and in vivo data helps us solve the problem of need of large amounts of data for building in vivo models to some extent, and also helps in reducing animal testing. The structural alerts identified by the in vitro models are very much helpful in interpreting the results. Here are the list of references. This concludes the session. Thanks everyone for attending the webinar. I'll be happy to take questions if any. You can also contact us later for further inquiries. Here is the email. Thank you.